Hi guys, welcome to ramanujan.math.circle, and today we're going to cover counting and number theory. So let's get into it. An introduction. So within counting, we will be covering basic counting, casework, and probability. And for within, we will also be covering complementary counting as a part of casework and things. You'll understand all the vocabulary that I'm talking about within the next hour or so. And for number theory, we'll be covering prime factorization and divisibility, as that shows up a lot on the AMC08. So without further ado, let's get into counting. Okay, basic counting. So there is an addition principle, or addition counting, basically, and it basically, the formal definition is if an event A can happen in A different ways, again, this is a variable, and event B can happen in B different ways, then A and B cannot both occur at the same time, which means they're kind of like independent of each other, and they cannot occur both at the same time, sort of. And then the number of ways of counting that A or B can occur is A plus B. And so what, for example, if we have, okay, so picking blue or green, right? So an item cannot be both blue and green. We're going to assume that's true, that there's no mix. It's either blue or green. So then you would add the combinations of blue and you'd add the combinations of green together. On that note, I will also introduce the fact that if A and B exists, so A and B can both occur, then you'd have to take a little different path. And what you do is you have to subtract for what is double counted. And for this, let me show you something called a Venn diagram. And many of you might have heard of this before, but what a Venn diagram is it looks like this. Let's say this is event A, this is event B. So this portion, this shaded portion over here, this is A and B. So when A and B both occur. This is when just B, and this is when just A occurs. Right? So in order to find the total possibilities, if you do just A, well, I'm going to say, A plus B, right? Because capital A can happen in A different ways and B can happen in B different ways. I'm going to say A and B can occur in C different ways. So if you do A plus B, well, that's equivalent to saying just A plus A and B, right, this area, plus just B plus A and B. But that's like counting A and B twice. So you'd like to get rid of one of them. And so as a result, you would subtract the middle part because you're double counting it. So it would be A plus B minus C, where A is number of ways A occurs. And that, this is number of ways B occurs. And this is the number of ways A and B occur. Okay. So now let's look at multiplication and counting. And if an event A can happen in A different ways and B can happen in B different ways, then the number of ways that A and B can occur is A times B. And again, so this is really important to know because this can be used to plug in and find the value of C that we talked about in the previous, in just a discussion. So these two principles are really important and you'd always want to remember them. And as time goes, you'll actually get these into practice. So let's start with a short example. How many 4-digit numbers are there? So this is a little, you might be thinking how this relates to addition counting or multiplication counting. So let me show you what I'm talking about. So 4-digit numbers, they basically have 4 digits, right? So these digits can be, well, 0 to 9, right? This can be 0 to 9, and this can be 0 to 9. This cannot be 0 because remember, the leading digit can't be 0, otherwise it's a 3-digit number, not a 4-digit number. So it can be 1 to 9. Okay. So we want the so our combination is we want the events that we want that happening. So it's event that the unit digit is a number that's 0 through 9. Tens digit 0 to 9. Hundreds digit is 0 to 9. And our thousands digit is 1 to 9. So we want all of these to occur. This is our event A, B, C, D. So these are events. And in order for all of these to happen, we're going to have A times B times C times D by the multiplication principle because we want all 4 to occur. And the number of ways that you can get the units digit to be a 0 through 9, there are 10 ways to do so because either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So similarly, lowercase b would be 10, lowercase c would be 10 as well. The thousandth digit being 1 through 9 is only 9 possibilities, so that's 9. So as a result, our total is 9,000. So there are 9,000 4-digit numbers. So that is the way you would apply the multiplication principle in order to find how many, for example, 4-digit numbers are there or things like that. That's the key process that you follow. Basic counting continued. So permutation, so we're going to go into some definitions. Permutation is the arrangement of numbers of a set into a sequence when you rearrange the elements, and the order does not matter. And the representation of permutations is NPR, or n factorial over n minus r factorial. Large majority of you did not understand what I just said. So let me explain to you what I mean. So the example we're going to take is when there's 3 different alphabets, A, B, and C. And we want it grouped together such that all of them are taken together at the same time. But so here order does matter. And so we want to see how many ways we can order the 3 letters. And there are a set number of ways you can do it, right? And as you can see, there's ABC, ACB, right? If you switch the order of the last 2. Then you could start with B, BAC, and then you could switch the order of the last 2, so BCA. You could also start with C, CAB, and then you could go CBA. That's 6 different possibility permutations. And note that ABC and CBA, for example, are not the same combination, same permutation, because their orders are different. The arrangement of the letters is different. So that's what a permutation is. Now, I mentioned something over here, and let me explain to you what that means. So NPR basically means kind of, in this example, it would be given and letters. So how could you, for example, arrange R of the letters? That's a good way of going about it. So that's how you would try to solve these problems. And now let me explain to you what factorial means. The exclamation mark, that's called a factorial. And so what factorial means, it's just, in definition, what it means is, so if you have n factorial is equal to n times n minus 1 times n minus 2 times n minus 3, and so on and so forth, till 3 times 2 times 1. So you multiply everything from 1 to n, all the integers, from 1 to n, and that's what n factorial is. Now, in theory, a lot of stuff cancels out in n factorial divided by n minus r factorial. But for example, if we were to go about solving this question with the ABC arrangements, so it would be, since there are three, right, so three letters, and we want to arrange three of them. So 3 minus 3, so that's factorial, is equal to 3 factorial over 0 factorial. And one important thing is 0 factorial is always equal to 1. So I would remember this too. And so it would be 3 factorial, and then that would be 3 times 2 times 1, which is 6. And evidently, these two are matching. So that's the way you go about doing permutations. On the other hand, we have something called combinations, where the order does not matter. So you're just picking out items. So that would be given, for example, n letters. How could you pick out r letters, arranging in any order? The order basically does not matter. So the representation of this is n factorial over n minus r factorial divided by r factorial. So this is the formula. And what this basically intends to say is that you don't account for the order in which you arrange the things. And so if you're picking out r letters, right? Every time you pick out r letters, how many ways is there to arrange these r letters, considering they're all different? If they're all different, how many ways? Well, you can arrange them in r factorial ways, right? Because our first letter can be r, there are possibilities, and once you take out 1, there are minus 1 left, then there are minus 2 left, so on and so forth, till, 2 times 1. So there are factorial. And so since order doesn't matter, the way you can remember this is you always have to divide out by r factorial, because we don't want to account for arranging. We want a smaller number. So the way you can remember which one is which is by thinking that when order does not matter, that means we don't account for arranging. So that means there should technically be, so if there's ABC, for example, you take this example, there's only one way of having a combination of ABC, but there are 6 ways of having a permutation of ABC. So that means permutations are always greater, and that means you divide less from, you don't divide as much from the n factorial and permutations. So that's how you remember, logically, that's how you remember which formula is for which. So yeah. And if this is not really clear to you, when we do the examples, this will become much more clear to you, because we're going to be applying these same concepts to the examples. Okay. So now we have something called casework, and that's basically where one splits a problem into several parts, and then several cases, and that's where the name casework comes from. And it is very widely applicable, and then you basically end up adding all the cases together to find your answer. So let's get into a short example, and I'll explain to you what casework looks like. So how many words are less than 4 letters long and contain only letters A, B, C, and D? And E, sorry. Here, word refers to any string of letters. So what that last sentence means is that it does not have to be a real dictionary word, basically. Okay, so the words are less than 4 letters long. Here, we're going to have something called casework. And what that means is we're going to have cases based on some criteria. So I think the criteria here is the length of the word, because based on the length of the word, you can have different ways of counting the number of words there can be. So I'm going to call the length of the word n. I'm going to say n is equal to 1, n is equal to 2, and n is equal to 3, because it says there are less than 4 letters long, and a word cannot be 0 letters long. So now we're just gonna try to solve for these cases. When n is equal to 1, that means there's just one blank. There's only one event, and I'm gonna call that A. And that means it, so actually I'm gonna call this event X. Yeah. A, B, C, D, or E can go in this blank, so that's 5 possibilities. Here, so there's an X event and there's a Y event. So here there are 5 possibilities, here there are 5 combinations. So for X and Y to occur, we use our multiplication principle, and we say, okay, so it's going to be 5 times 5, because this is the number of lowercase x and this is lowercase y, for example. So that would be 25. And then here we have x, y, and z. And each one of these has 5 possibilities because they can either be A, B, or C, or D, or E for each one. No restriction. So we're going to apply our multiplication principle again. So x and y and z. And for that to occur, it would be x, y, z. And that would be equal to 5 times 5 times 5. And that's equal to 125. So now we have our cases and we have the answers for each of our cases. And according to Casework, then you add all the parts together to get the total. So you add 125, 5, or 25, and then 5. And when you sum it up, you get 155. So there are 155 words that are less than 4 letters long and contain only the letters A, B, C, D, and E. And remember, there's no restriction on how many times a certain letter has to occur. So that's why we can apply the multiplication principle pretty well. Okay, so now there's something called complementary counting. And what it basically means is you count the, so instead of counting what we want, we count the total number of possibilities and we subtract out the part that we don't want. And so the biggest hint to do that is when you have the phrases at least or without. And that indicates that you should apply complementary counting. And when the cases that don't work are less than the number of cases that do work, then it also is very useful to apply complementary counting. All right, so let's do an example. How many 4-digit positive integers have at least one digit that's a 2 or a 3? So actually in a previous example, we figured out already based on the multiplication principle how many 4-digit numbers exist. And if you recall, we just said, okay, there are 4 digits. And they are, so what is it? So this can be 1 through 9. This can be 0 to 9. This can be 0 to 9. And this can be 0 to 9. So based on our multiplication principle, it would be 9 times 10 times 10 times 10, which is 9,000. So that's our total number of 4-digit positive integers. Now they're asking for how many 4-digit positive integers have at least one digit that is a 2 or a 3. So our complementary, so our it would be hard to count every single number that has at least a 2 or a 3 because it could have a 2 and a 3. It could have just a 2, it could have just a 3. It's too much work. So now what we're going to do is we're going to figure out how many numbers have neither a 2 nor a 3, because that's definitely not going to meet the condition. That's the opposite of the condition. And what that would mean is this digit over here can be 1, it can be 2 or 3, and then it could be 4 to 9. So this one can be 1, and then it can be 4 to 9. Sorry, this can be 0 as well. And this can be 0, 1, and then 4 to 9 as well. And then this one is just 1 and then 4 to 9. So what that means is our multiplication principle gets used again. And this is a total of, for this event to occur, i.e. the units digit to be 0, 1, or 4 through 9, that would be 8 possibilities, 8 ways of happening. And then for the tens digit, that event to be, the tens digit to be either 0, 1, or 4 through 9. That is 8 ways of happening. And same with the hundreds digit event. So that's 8 ways of happening. And for the thousands digit, we have 7 ways of happening. So applying the multiplication principle, we get 7 times 8 times 8, which is a number which appears to be 3,584. And then, so now that's like the cases that we don't want. So we have our total, which is 9,000. We're going to subtract 3,584 from that because that's how complementary counting works. And if we do that, we get that the total number of positive 4-digit positive integers with at least 1 digit, that is a 2 or a 3, to be 5,416. And counting through a bunch of cases and coming up with that huge number would have been a real pain. So it's really important to apply the technique correctly. And like I said, the word at least and with or without are very useful. And here we have the word at least. So that's a hint that you want to apply complementary counting. So kind of last idea in counting, but probability. Probability, many of you might hear, oh, what's the probability of it raining? What's the probability of weather is a huge place where probability happens? What's the probability that or what's the chance that you get a tails? What's the chance that you pull out a blue sock? So there are different things like that. And so probability is really a sense in our life. You probably, if you think about it, you have seen a lot of instances of probability. And mathematically, it's often described as the favorable outcomes over total outcomes. And what I mean is favorable outcomes is what I want. So what I want. And this is what exists, right? And so that's like the total. So it's what I want divided by what exists. And usually you can use like counting principles, like for example, complementary counting. You can use that over here. It's called complementary. Here it's called complementary probability. And what it is you subtract the probability that you don't want something. So I'm just going to call this probability you don't want. And this P and parentheses, so okay, this means probability of X. So that's the formatting I'm using. So probability of don't want and 1 minus that. And why am I doing a 1 minus? For those of you that are new to probability, let me introduce to you one simple concept. Probability of a thing occurring, the maximum it could be is 1. That's the maximum. And so probability is always between 0 and 1 inclusive. And the sum of the probabilities of a certain event occurring is always, so if there is, let's see, what I want plus what exists. Okay, so what I want plus what I don't want divided by what exists should be equal 1. And what I mean by that is, so what I want divided by what exists, right? If I sum this with what exists and then what I don't want, I am assuming everything is either something I want or I don't want. So it actually, if what exists, right? If everything is something I want or I don't want, then this becomes what exists over what exists, right? Because everything. And that's equal to 1. So that's why you subtract what you don't want from 1, because the total of the probabilities is always 1. And so now let's you can also use your addition and multiplication principles like you did, and you can use that for probability. So now let's do a quick question. What is the probability that all four fair coins are to be flipped? What is the probability that all 4 will be heads or all 4 will be tails? So here, indeed, we're going to be using both multiplication and addition principle. So let's get to it. So the probability of heads is half. The probability of a tails is also half. So we want the probability that, so we're going to split it into 2 cases, all heads and all tails. Okay, for all heads, we're going to have 4 events, right? And each of the 4 events are 1 flip each. Okay, so the first event is you want a head, and you're flipping a coin. So that's half probability. So the probability is half for event A, which is the first flip. Event B is the second flip, and that also has a half probability of getting a heads. Event C has a probability of half again of getting heads, and event D also has a probability of half. Since you want all 4 events to occur, meaning all 4 of the coins need to be heads, you're going to multiply these, and you get this is 1/16. So similarly, we can do the case for all tails. So there are 4 events again. I'm going to call them W, X, Y, and Z. So it's a first flip, second flip, third flip, fourth flip, because each of the flip, you have half a probability to get tails. We want all 4 of them to occur, so we're going to multiply, and that's 1/16. So here there is a probability that all 4 will be heads or all 4 will be tails. If you remember from our addition principle, when you want 2 things to occur and they both can't occur at the same time, then you can add the 2 ways of counting ways. So here you're just going to extend that same thing to probability, and you're just going to add the probabilities. Obviously, there can't be 4 heads and 4 tails for 4 flips. So what we're going to do is we're just going to add 1/16 from the first case, 1/16 from the second case. We get 1/8 from that. So the probability that all 4 will be heads or all 4 will be tails is 1/8. So here we actually apply the addition principle, the multiplication principle, as well as casework. So this is a really good problem to understand and get into a glimpse of probability. So now let's look at our first example. How many words can be formed from all the letters of the word daughter such that the vowels never come together? So I'll give you guys some time to solve it, and then we'll come back and discuss this question.